So with our first test coming up this week, and our first chance at distance learning this week as well, I figured it would be a good idea to make a video reviewing all the content from the chapter, so that way you have it as a study tool. I know we didn't get to as much review in class as I would have hoped, so hopefully this is a good substitute. So in chapter 1 in general, we kind of talked about a whole bunch of different things, right? Sequences, series, proof, the binomial theorem, kind of just a whole mashup of topics that all kind of fall under this umbrella of discrete math, kind of just these miscellaneous extra topics. So the first thing we talked about is just an overview of sequences and series, right? How we use the notation, some of the different tricks we use to come up with the rules for these sequences and series, and just kind of what it all means. So a sequence is just a list of numbers that are usually written, or have to be written, rather, in some kind of defined order. Right, so I can't just list whatever numbers I want, and however I want, I have to put them in some kind of order. So for example, maybe I have 3, 8, 13, 18, 23, and so on. Right, so these are clearly written in some kind of order, right? These are written in ascending order. They are written with some kind of a general rule in mind, and I'm going to come back to what that means in a minute. Each one of these is called a term. Right, so those are all terms. 3 is a term, 8 is a term, 13 is a term, they're all terms. And they all abide by some rule, right? To get from term to term, I add 5 every time. And you can see that I do that every single time. Well, I can write this general rule. We have some kind of a rule here. I can write that in this notation in brackets a sub n. So a sub n is my way of writing what my rule is. In general, we can be more specific as we go on. We're going to talk about later on what that rule means and how we actually come up with it, but for now, we're going to see that this sequence obeys the general rule, should be 5n minus 2. So we'll talk about how I came up with that later. Hopefully, if you remember some stuff from the beginning of the chapter, that first quiz we had, you'll know how I came up with that. So we have terms. Sometimes we also call a sequence a progression. You may see both in our book and on the exam, but in my class, in my tests, you'll always see sequence. So that's a sequence. A series is just adding up all the terms of the sequence. So this is just a sum of terms in a sequence. I'm going to move my little sigma notation down here so I have some room to write. And the way we can do that shorthand is with, as I kind of just said, with sigma notation. So I have a few different parts here. This first part is called an index. And the index can be a lot of things. Sometimes you'll see I for index, right? So I no longer just represents the complex number, but it also can be used for our index, but you can see anything. So here I'm using n. Sometimes you see k, r, whatever. As long as you're consistent, as long as you're precise, it really doesn't make a difference. My summation, I have to tell my summation how far I'm going, right? Where my starting point is and where my ending point is. So this index has a lower bound, my starting point. So my starting point, and an upper bound, my ending point. The Q didn't move with the sequence. So the upper bound, ending point. And as always, I have some kind of a general term. This is the same idea as the general term I had in my sequence. So if I actually wanted to calculate this sum, I could do that in exactly the way I would listing out all of the terms in my sequence. So I'm just going to plug in when n is 1, and I'm going to get 1, and when n is 2, and when n is 3, 4, oops, this is not a sequence. I'm adding all my terms together. So I left off at 1, 2, 3, n is 4, I get 7, n is 5, and then n is 6. And of course I would want to add all of these together. So I'd get 4, 9, 10, and 16, should be 26, 24. I'll check that before I go on. Don't want any mistakes in this video. 7, 9, and 11, 36. Close. So both a sequence and a series can be finite or infinite. And a finite series or sequence just has a defined number of terms. And of course an infinite series does not. An infinite series has infinitely many terms. The sequence or the series continues on forever. Of course, the way we show that is with our ellipsis, our dot, 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 which is, if you remember from the beginning, what I did up here, to say that this series, the sequence 5n minus 2, is going to go on forever and ever and ever and ever. And that was really what was important in 1.2, sorry, in 1.1. 1.2, we took this a little bit farther, talking about a specific type of sequence, and that was an arithmetic sequence. And for an arithmetic sequence, the key here, no matter what I'm doing, is I'm just adding. So we have our general term, and you can see that addition right here. All of our a's mean the same thing, right? So this would be my nth term, just like it meant in 1.1. So of course, this is my first term. And then d, well, d is new. D is my common difference. So what my common difference is it's some kind of a constant value, right, that I'm adding on multiple times to my first term to generate every next term of the sequence or the series. The number of times that I'm doing that is given by this n minus 1. So why n minus 1 is kind of the question that tends to come up a lot. And the reason is if I look at a series and if I write it out exactly the way it shows up in my general term, so I haven't tried to simplify this algebraically or anything. So maybe I have 3, and my common difference is 2, so I have 2n minus 1. So if I list out just some n's here, we'll just do the first 4 terms, and then we'll talk about what happens when I get to the nth term. Well, my first term is 3. My second term is going to be, well, 2 minus 1 is 1, 1 times 2 is 2, plus 3 is 5, and then 7, 9, and so on. So if you notice, for my first term, I didn't have to add 2 at all, but to get to my second term, I had to add 2 once. And then to get my third term, I added 2 twice, and then 3 times, and then so on. Or there's always one less n than the term number I'm on. So if I got all the way to my nth term, I've started at 3, and I've added 2 one less time than the number of terms that I've listed. So that's kind of where I'm getting this n minus 1 from. And that's going to come back over and over and over again, kind of throughout this whole chapter, or at least through the whole sequences and series part of this chapter. So the next thing we talk about is a sum. Right? If I'm going to talk about a sequence, I should probably also talk about its series. And everything means the same here. So right, n is my number of terms. And of course I have my first term and my last term. And of course S for sum. So the sum of n terms, right, I take the first term and the last term, I add them up, and I multiply that by half of the number of terms I've had. We actually proved why this works in our book. We did this in class, so you can kind of go back to your book to review that. And in hindsight, maybe I should have used that this little trick right here to calculate my series from before. Actually, let's do that. So just to practice it, right, if I want to look at the sum from 1 to 6 of 2n minus 1, well, instead of listing out all my terms and adding them together, because it obviously took a little while before, I can use my shortcut, right? I have 6 terms, and my first term is 1, and my sixth term is 11. All right, so 6 divided by 2 is 3, 1 plus 11 is 12, my sum is 36. So for this next problem, if you want to try it on your own, you can pause the video, but I'm going to walk through it here. So one of the things we can do is play around with these formulas, use them in different ways. So I have this. The first term of an arithmetic sequence is -7. Right, so my first term is -7. I'm going to write that out, seems important. And my fourth term is 23. Fourth term is 23. If the sum of the first n terms is 689, find n. Find the number of terms. So the sum of n terms is 689, and I want to know what n is. Well, I have some formulas I can use. I have formulas at my disposal. This will be helpful. So I can say, well, a sub 1 is -7. That's great. A sub 4, well, we can use our formula to use our, where'd it go? Our general term formula to express my fourth term, right? So this is going to be a sub 1 plus, I'll write it out all in general right now, times d, right? We don't know what our common difference is yet, but that's okay. We can solve this. I'm actually do that right now. Right? Well, our fourth term is 23. Our first term is 7 plus 3d. And by solving this, we know that d then is 10. So we're going to hang on to that for a minute. I know that the sum of my n terms is 689. Right, so if I want to use my formula, right, n over 2, my first term plus, well, whatever my nth term is, and I need a way to figure that out. Well, I've got all the pieces I need to figure that out, right, because I know my first term, I know my common difference. So just to kind of sidebar here, a sub n is a sub 1 plus n minus 1d. So I have -7 plus, well, we don't know what n is yet, so we have to leave that alone. D is 10. So I get 10n minus 10, so I have 10n minus 17. And that's going to go in for my a sub n. So doing some simplification, doing some distribution in a minute, I'll have 10n minus 24. If I distribute, move some things over, I get 5n squared minus 12n minus 689. And believe it or not, this does factor. I'm just going to move up here so I have some room. Right, this is going to factor into, check my notes too, I have 5n plus 53 and then n minus 13. So of course this is going to give me n equals -53 over 5 and 13. Well, the only answer that I care about is the one that's a positive integer, because I can't count to -53 over 5 relatively nicely, so that's going to go away. And the only case I have is n is a positive integer, so n is 13. So on to 1.2, part B, we talked about geometric sequences and series. And just like before, I have a general term, right? And they all mean the same thing they did before. So my nth term, or my general term, my first term, and this is new, right? R is my common ratio. The difference being that with geometric series, instead of adding, we're multiplying. So common ratio is my constant. How did I word it before? So it's just some constant value. Then instead of adding on, I'm multiplying on this time. All right, so if I had a sequence and it was given by maybe 3 times 2 to the n minus 1, right? My first term then is 3, and my common ratio is 2, so I'm multiplying by 2 every time, and so on. Well, one thing we can do, just like we did with arithmetic sequences, is we can find its sum, but I have to be careful. I have two different cases. So for a finite geometric series, and that's just what GS means, I have this formula here. So I'm going to take my first term, multiply by 1 minus r to the n, and divide by 1 minus r. So this is for a finite geometric series. So I have to be careful here and know which one to use and which one to not use. If we want to talk about an infinite geometric series, we have a couple of conditions we have to talk about. So the first one, the biggest one being this r less than -1 case. So what happens is an infinite geometric series only has a sum if it actually approaches a number, and we call that converging. That's not where I want to put that. I want to put that over here. So it converges only when this common ratio is less than 1, or the absolute value of that common ratio is less than 1. So what happens if I were to take this and look at the sum? So if I do, actually if we just look at 1/2 to the n, and I also keep track of the sum of all those terms, right, when n is 1, well, actually we'll do to the n minus 1 just to be consistent. So I get 1, my running total is 1, 2, so I have 1/2, my running total is 1.5, get 3, 1/4, my running total is 1.75, and so on. Well, this number is never, it's going to get bigger and bigger, but it's never going to get infinitely bigger, right? It's not just going to grow without bound, as we say. It's going to actually approach a number. That number is going to wind up being 2. So even if I were to extend out like infinitely many times, or in this case just 100 times, I'd have whatever 1/2 to the 99 is, but my sum would get closer and closer to 2 if I were to add up all of those terms. And that's what this is saying here with my sum of an infinite geometric series, is that because my common ratio is less than 1, I can actually find the sum of this infinite series. So to finish my example, my first term is 1. 1 minus 1/2 is just 1/2, and I would get 2. So we say the sum converges to 2. So it approaches 2. It never always gets to 2, but it's going to get really close, or it's going to look like it got there. And this is actually going to set us up for when we talk about limits in Chapter 4. The other thing we talked about in 1.2 Part B were applications. So, and the trick with applications is we need to be able to read this problem really carefully. I want to be really careful when I'm working this problem because there's a lot of information, and trying to figure out how to use that information can sometimes be challenging. So same thing, if you want to try the problem on your own, you can just pause the video here and work it out. But I'm going to go right on and go through it. So it says Joey started working at Citizens Bank in 2015. He earns an annual salary increase of 2.5%, so that seems important. Underline this. And then in 2020, you know that Joey's salary was $58,823, so that seems important. I'm going to write it off to the side. So in 2020, he earns $58,823. His salary increases 2.5% every year. And I want to know, what is his starting salary? Okay. Well, because it's a percentage increase, because I have a percentage increase here, this is going to tell me that I'm actually working with some kind of a geometric series, not an arithmetic series. And that's because I'm not adding a fixed amount every time. I'm adding, I'm adding on a fixed proportion of the term before, rather than just a constant amount every single time. So the first thing we should do is figure out how to actually represent this as a geometric series. Well, looking at the given information that I have, if I started working in 2015, right, and I'm going to call that my first term, so n equals 1. So if n equals 1 represents 2015, then I need to know what number is going to represent 2020. Well, in this case, we can just count up, right? 2015, 16, 17, 18, 19, 20, 20. That's n equals 6. So that means my sixth term is equal to 58,823. I can also represent that using my geometric series. So we don't know what the first term is. But we know that if I'm increasing my salary by 2.5%, that means I'm going to multiply my salary every single year by 1.025. Right, so that increase tells me it's going to be 1 plus the percent. So maybe we'll make a note of that off to the side. So if it increases, it's 1 plus whatever the percent is as a decimal. Of course, if it were to decrease for whatever reason, I wouldn't want my salary to decrease, but if it were to decrease, it would be 1 minus the percentage as a decimal. So we can actually simplify this a little bit. Actually, I should have fixed this up here. N is 6, so R is 5, or N minus 1 is 5. So we have, I don't need these equals, we have 58,823 equals whatever 1.025 to the fifth is, so that's going to be approximately 1.1314. It should be good enough for now to estimate it. And then my last step is just to divide. So I get a salary of approximately $52,000, and that nice round number would be good enough. Since after all, in real life, our starting salaries are usually nice round numbers like that. We'll accept that as our final answer. All right, so moving on to 1.3 part A, we talked about, this is where we started talking about all these different proof techniques that we have. We started talking about direct proof. So for direct proof, if I have an even number, some of the strategies we learned were that if I have an even number, I can write that at whatever even number I want is 2 times k, 2 times some integer k. Right, no matter if I need just whatever even number I want, I can always make an even number by taking any number I want and doubling it. If I want an odd number, I can double my number, my integer, and add 1. Sometimes you'll see that as subtracting 1 instead. Kind of whatever one is more convenient, that's what we go with. But in either case, k still has to be an integer. And the reason that we know it's plus 1 is by something we call parity. And all parity is going to tell us is that some number n can either be odd or even. Can't be both. And it alternates. Or I'll say it this way, I'll say consecutive integers alternate. Integers alternate odd and then even, right? 1 is odd, 2 is even, 3 is odd, 4 is even, and it just goes back and forth. So all I'm trying to do with direct proof is really just get from point A to point B, right? Trying to get from my left-hand side, my point A, to my right-hand side, my point B. So it's best to do this by actually just writing down your left-hand side or one side at a time, so that way we don't kind of get confused. We don't want to get lost. I'm just going to keep that right-hand side in the back of my mind, so that if once I get to that point, or if I get stuck, I know I can go back and consider that side. But we're just going to treat part B as my goal. We're not going to do anything with it right now. Well, I kind of just need to play around with it, right? What can I do to this to get from one side to the other? Well, I can probably start by squaring these terms here. So a plus b squared, we know is going to look like a squared plus 2ab plus b squared. And then a minus b squared is going to be a squared minus 2ab plus b squared. All right, well, next step is going to be, what can I do next? Well, the next obvious thing to do, I think, would be to combine like terms. So I have 2a squareds, my 2a plus my 2ab's cancel out, and I have 2b squared. Keeping in mind our goal, I need to find some way to get that 2 outside of the sum, so I'm going to factor out a 2. We notice that that is exactly equal to my right-hand side, so since I've got my left hand and right-hand side equal, I'm done, and that's where that little box comes into play. When we did contradiction, we're going to use contradiction when we have some kind of what we call a binary choice. And that really just means it's either something, right? Say it's either odd or it's not, right? There's no third option. There's no both. There's no neither. Right? It's either odd or it's not odd. It's either rational or it's irrational. It can never be both. It can never be neither. It's this or it's that. And usually what happens is we know more about one of these conditions than we do the other. So our steps for solving contradiction is to say, well, first of all, what's going on in the problem? What's being implied by this statement? And then we're going to take that statement and assume the opposite is true. Usually because we know more about the other situation than we do the one we're given to work with. But we also know along the way that the assumption I made is being made to be disproven. I'm trying to work until I get to a contradiction. The fancy Latin phrase for this is reductio ad absurdum, and that literally means reduced to absurdity. So other than sounding like a Harry Potter spell, it means we're going to work this thing out until it gets to the point where it's absolutely ridiculous to consider my statement true. So here's my example. We're going to prove that no real number exists such that 1 over x minus 2 is equal to 1 minus x. And again, if you want to solve the solve the problem on your own, now would be a good time to pause the video and try it for yourself. So we're going to prove that no real number exists. Well, it's a lot of work to try every single real number. Actually, it's impossible because there are infinitely many of these. So what's going on here? The implication in this problem is that there does not exist a real number. So we assume the opposite to be true. Assume that there does exist a real number. And actually, for the sake of being formal, we're going to assume that there's some specific real number other than the one that's being used in our expression. So we'll call it A. So we're going to assume that there is some kind of real number such that my statement is true. And sometimes in these proofs you'll see it say assume for contradiction. Sometimes you'll see it say just assume. Either way we can go with it. Well, step 3, we're just going to use a direct proof now. Right, that was my step 3 before. Use a direct proof to arrive at a contradiction. So we're going to work off of this assumption, and maybe the easiest way to solve this then would be to actually solve it. So we're going to get rid of this rational expression here. I'm going to FOIL. I have negative a squared. I have plus 2 plus 1, so plus 3a minus 2. Subtract 1 on both sides. 3a minus 3. And well, this is not factorable, so the quadratic formula would probably be helpful. So we're going to say that a, well, we'll use my quadratic formula here, so opposite of 3, plus or minus the square root of 3 squared is 9, minus 4 times negative 1 times negative 3 is negative 12, divided by 2 times a. We already know this is going to be problematic, right, because I said that a had to be a real number, and there's no way that I can have a real number if my discriminant is negative, right? I can't take the square root of a negative number. You can't take the square root of a negative number and still have a real solution. But we had to assume that we had a real solution, but we don't, right? And this is where we get our contradiction. So I'm going to say this is a contradiction. I'm going to move the rest of my notes down for a minute just so I have a little bit more space. This is a contradiction. Our assumption is false. And then therefore our original statement must be true. So therefore no real number x exists such that 1 over x minus 2 is equal to 1 minus x. That's the end of our proof. So we're working until we get to a contradiction and then working it out all the way. With the counterexample, all I'm looking for is just one example. I don't need to do anything crazy, except I need to maybe move this down a little bit. One example. All I got to do is say, here's the statement I'm given. they're assuming that it's categorically true, but I can come up with an example that shows you that it is not. So my example says, if n is an integer and n squared is divisible by 4, then n is also divisible by 4. Again, pause the video if you'd like to try it on your own. The first counterexample that I could come up with is to let n equal 6. And what happens when n equals 6 is n squared is 36. 36 is divisible by 4. But 6 is not divisible by 4 at all. So this one counterexample is enough to disprove the statement that I was given, to assume that it was true, to say, oh, the statement is definitely true. Here's my example, n equals 6. That tells you, no, it is not. So that's contradiction and counterexamples. The one catch, maybe I'll put it over here, is that you cannot use a counterexample during a proof by contradiction. During a proof by contradiction, because it's almost like a double negative, right? It's like saying, we're going to assume it's not true. Here's an example that shows it's not true. Well, all you're really doing is showing me an example that shows that the original statement works. So that's not really proving it, other than just demonstrating that the property is true. So you cannot ever use a counterexample during a proof by contradiction. You have to use a direct proof. The last type of proof we talked about was proof by induction, and there were 3 steps here. But first, when are you actually going to use a proof by induction? Well, you're going to use a proof by induction when you need to count different cases. And specifically when there are too many cases to count. Right, if I have just a finite number of cases, like maybe there are 5 cases, I can just check every single one. But here, it wouldn't really be possible to check, say, all of the natural numbers, right? There are infinitely many of them. I could just count them. I can't count them up and be done at some point. So the other thing we run into with induction is that with induction, I said we were moving from general, that's deduction. With induction, we're moving from a specific case to a general case. Now, along the way, we have to make some kind of an assumption about the premise. And that's different than what we've been doing, right? We've been doing what we call deduction, which I kind of just hinted at a second ago. And with deduction, we're moving from a general case and using those general things I know to prove a specific case. Right, so induction is going from specific to general, and the steps kind of outline that, right? My base case is usually going to be for n equal to 1 unless I'm told otherwise. And that's my specific case, right? Here's my specific case. Prove it for n equals 1. This is kind of my groundwork, saying, yep, my specific case works. We can kind of move on from here. If I can show that it works once, I can hopefully show that it works all the other times. Step number 2 is to assume that the statement is true for some number of cases, right? We're trying to prove it's true for, say, all integers or all natural numbers. So we assume that it's true for some number of those cases. And then we're going to prove it for the next case, and to say that if it's going to work for, say, the next case, it's got to work for the ones all before that. So we have specific case, base case, we have assumption along the way, number 2, and then we have general case in step number 3. So our example, kind of a classic example, is to prove that the sum of n consecutive integers, that's all that's saying on the left, is equal to this n times n plus 1 divided by 2. So let's get started. And this is for all positive integers n, so I'm going to start with the smallest possible case I have, and that's n equal to 1. Just like we can usually default to and assume. So on the left-hand side, this is just the sum of n positive integers, consecutive integers. So on the left-hand side, the sum of one consecutive integer starting at 1 would just be 1. On the right-hand side, I'd have 1 times 2 divided by 2, which of course is also 1. So my base case works out. Specific case is good. We need to make an assumption along the way, and that's what we're going to do right here. So my assumption, rather I'm just going to come out and say it. I'm just going to say assume that 1 plus 2 plus 3 all the way up to some number k is equal to k times k plus 1 over 2. So it really just looks like I'm replacing an n with a k, and functionally that's all I'm really doing. Formally, I'm trying to make sure I just don't mix up my variables. So anytime I introduce a new letter, a new variable, I need to tell you what kind of variable it is. And now I can actually use it. So my assumption is going to be used to prove, hoping I have the space, is to prove that this is true for k plus 1. And anywhere I see a k, I'm going to change it to k plus 1, so even k plus 1 turns into k plus 2. And in order to do this proof, I need to use the assumption I make along the way. So it would be helpful if I could actually make it crystal clear where this assumption was going to come into play. And with a sequence, I'm going to do that by actually writing the term before. So I didn't actually do anything here. I could really, if I wanted to, list out as many terms as I want. We're just saving ourselves some time. But here, we want to make it really clear, right, where that assumption is going to get used, right? This right here that I highlighted is the assumption that we made in number 2. So I'm going to use that there. So that way I can say this is k times k plus 1 over 2, and I'm bringing down my k plus 1 from before as well. I can combine these fractions, right? I can say this is k times k plus 1 plus 2 times k plus 1 divided by 2. I can distribute, or I can just factor out a k plus 1, which should save me a considerable amount of time considering I'm done with the proof. So step 3 is just a direct proof that uses the assumption we made in step 2 along the way to get to that point. So that kind of ends our proof section. This is a super important topic for IB. This is a super important topic in mathematics. This kind of lays the groundwork for a lot of exploration that we do, for a lot of theory work that's done, a lot of research that's done. It all comes back to these 3 types of proof. So in section 4, we talked about 2 things. We talked about counting principles, and we talked about the binomial theorem. And we started by talking about what a factorial is. It's not just a whole bunch of excited numbers. That's what the exclamation points look like. It's really just our shorthand form of saying I'm going to take a number n, and I'm going to count down all the way until I get down to 1, and I'm going to multiply all those numbers together. So if you remember our product notation, our pi notation, from when we talked about sum and products of roots, another way we can actually write this, not from 0, should be from 1, is to say it's just the product of all of the integers from 1 to n. Either way, it all means the same thing. So we can actually use this to simplify, because we have these like counting backwards ideas, right? So my rule of thumb is to not work on the problem before I tell you what to do. My rule of thumb is to expand the bigger factorial every single time. Well, so which number is bigger? That would be 5, right? Not 3. So I'm actually going to count backwards from 5 until I get to 3 factorial. Right? Because I can say at any point I'm going to stop. And that exclamation point for factorial is going to tell me, realistically, I'm going to keep counting backwards. But for the sake of showing the cancellation, I don't need to write it all out. And that's what this is doing right here. It's the same type of thing with n plus 1 factorial divided by n minus 1 factorial. And again, pause the video if you want to work this one out on your own. I'm going to take the bigger factorial. In this case, again, that's going to be n plus 1 in the numerator. Doesn't always have to be in the numerator, but in this case, they both were. And I'm going to count backwards until I get to n minus 1 factorial. just to make it crystal clear where my cancellation is, right there. I realized I didn't simplify this problem before. I get 20. And over here I get n times n plus 1, or if you feel so inclined, n squared plus n. We're going to come back to this in a minute. One of kind of the key principles that we're going to use moving forward that we didn't really talk about yet, and that the book doesn't really talk about, is the fundamental counting principle. And that's to say that if I have, say I have A ways to select, let's say from category A, and so if there are A ways to select from category A, and I'll say B ways to select from category B, and really I can extend this out as far as I want, then there are A times B ways to select A and B, say like one shirt and one pair of shoes, and A plus B ways to select A or B. So say like one shirt or one pair of shoes if you're out shopping or something. So when we talk about permutations, then we're talking about some kind of an ordering. And the key here is that with permutations, order matters, and this is where every single math teacher that has ever walked the face of the earth has looked at his students and said, your combination locks are not really combination locks, your combination locks are permutation locks, because the order in which you put the combination into your lock matters. If I am ordering all n objects that I have, for however many objects that I have, then it's just n factorial. If I have, I don't know, 6 people in line, and there are 6 factorial or 720 ways I can line them up. But if I'm making a choice, so if I am ordering R objects, so I have R things that I've selected from n distinct objects, so I'm not counting duplicates here. Not doing an example yet, then I have this NPR notation. In this NPR notation, the formula is going to be n factorial divided by n minus r factorial. And I had you guys do an investigation talking about or showing how we come across or come about this formula. Right, and we know that we can actually use our calculator for this. My example might be to say if I'm going to place or pick 3 people in, let's say, like some kind of a leadership role. So maybe I have like a president, vice president, or like secretary from a group of 7. Well, then I have 7p3, which is the same as saying 7 factorial divided by 4 factorial. Right, 7 divided by 7 minus 3 is 4. So if I put that, I can either do that out longhand, or fortunately our calculator can do it for us. And I get 210 ways I could do that. So the way I remember it is for permutations, I remember P for place or position, right? The position or place that I put you in actually matters. With combinations, that's not the case. With combinations, the opposite is true, and the order does not matter. Does not matter. Regardless of how I'm choosing them, so you notice I said choose instead of order. So if I'm choosing R objects from n distinct objects again, so I don't have this duplicate type of work again. Then we have, put it down here, I have NCR, or sometimes you see it written this way. And either way, the formula is n factorial over r factorial and minus r factorial. And you might be wondering where I'm getting this from, where this r factorial is starting to come into play. You might notice that part of this formula looks a lot like the permutation formula. I'm going to come back to that. For now, what I remember for C, I remember C for choose, meaning it doesn't matter what order I choose you in, it's all the same group. So my example. So I'm choosing 3 students from a 5-person student council to attend some kind of a service trip for the council. And I'm going to put them in 3 different positions. I'm going to give them the role of manager, coordinator, and driver. So one person's going to drive everybody, one person's going to coordinate the trip, and somebody's going to manage it while they're there. And I want to know how many different ways I can order that grouping. Well, in this case, the ordering matters. Right, the ordering matters because if I put a group where A is the manager and B is the coordinator and C is the driver, well, that's a different group as if I gave B the manager position and A the coordinator position and gave C the driver position, right? It's a totally different group with A as the manager versus B as the manager. So this is a permutation. So I'm going to say from 5, I'm not choosing, I'm picking or placing 3. So I can use my formula, or I can just do it on my calculator, but either way I'm going to get 60 different ways that I can order my people, my students. Now the difference is between problem 1 and 2 is now there are no roles being assigned. I'm not assigning roles. So if I actually duplicate my list here, I'm not sure why that came along with it, there are no more positions. Let me cross it out. So there are no more positions. So a group of A, B, C and a group of B, A, C are exactly the same position. Right, so we need to find a way to eliminate all these duplicates. Right? Order does not matter. Which tells you it's a combination. Well, I need a way to get rid of the duplicates. Well, the first thing I might want to look at is just in general, how many different ways could I put them in orders, right? And that's still a permutation. That's 5 pick 2. But now I need to eliminate all of these duplicates that I have. And that 3 factorial, that remember up here, right? This r factorial is my way of getting rid of all these duplicate groups that I now have, where A, B, and C and B, A, C, those are the same exact grouping. So that 3 factorial that I'm adding in there, that's my consideration. That's my way of getting rid of that group, those duplicates. And I have 10 ways now that I can do that. The same idea gets applied to this next problem. Again, as usual, if you want to try this problem on your own, you can just pause the video right here. But I'm going to go ahead and solve it now. So we have 8 boys and 5 girls on the math team. I need to pick a team of 6, but the condition is that there has to be at least 2 boys and 2 girls. So I think the best way to tackle this problem would be to draw it out. Say I have 6 different positions, 6 different slots I can put students in. I need to have 2 boys, I need to have 2 girls, and the remaining 2 spots can be either. So what are my cases? What are my options? Well, in the first case, both of those missing positions could both be boys, right? So I'd have 4 boys and 2 girls. Or they could both be girls, so I'd have 2 boys and 4 girls. Or I could take one of each. So I'd have 3 boys and 3 girls. So, well, if we kind of break this down a little further then, the order in which I pick the boys doesn't matter. If I've got the 4 boys right there in the group, it doesn't matter who I select first because I'm just talking about a team of 6. So this is a combination, and it's going to be from 8 because I have 8 boys. And I'm choosing 4. And I'm also choosing 2 girls from 5, so 5 choose 2. And because I'm picking 4 boys and 2 girls, it's an and, so my fundamental counting principle tells me I'm going to multiply these together. And there are 700 ways I can do that. Well, so that logic is going to continue for my other 2 cases, right? I'm picking 2 boys or choosing 2 boys from 8. I'm choosing 4 girls from 5. And since I'm picking 2 boys and 4 girls, I'm multiplying my combinations and getting 560. I do this here. I'm choosing 3 from 8. I'm choosing 3 from 5. I'm getting 140. Now the last question is what to do with these 3 numbers. Well, I can have case 1 or case 2 or case 3. So I'm just going to add all these numbers together. Right, I have 700 ways I could choose case 1, or I have 560 ways I could choose case 2, or I have 140 ways I could choose case 3. And that gives me 1,400 ways total that I could pick my team. So finally, we have one last topic, and that's the binomial theorem. And it's kind of unrelated to this section, and it's also kind of not. On the surface, it looks unrelated, but the reason I say it's also kind of not is because my formula includes those combinations that we were just talking about. So my formula looks a little bit gross, but it's not as bad as it looks. So all this is saying is if I have a binomial here raised to some natural number degree, so I've got some kind of positive whole number, I can actually expand it and write it as a sum. I can write it as a sum of some combination from n choose r. I take my first power and I raise it to the degree minus whatever term I'm on. So the way I like to remember that is to say that I'm counting down from n. In my last term, I'm just raising to whatever number term I'm on, and it's going to count up then. It's going to count up from 0 to n. Of course, this is from n to 0. The shortcut we talked about, actually I don't want to change colors yet, the shortcut we talked about was use Pascal's triangle. We said that all of my combinations actually map right on to Pascal's triangle. So actually move this down. And we should be able to generate these by now pretty quickly on our own. Remember that my first and last term in each row is a 1, and then every subsequent term is made up by taking the 2 terms above it and adding them together. So here, 1 plus 2 is 3, 3, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc. The trick is just to remember that we're going to start counting our rows from 0. So my row of just 1, 1, my solitary 1 is n equal to 0. And then 1, my second row is 1, 2, 1, my third, fourth, and fifth row. If you're ever stuck, notice that the number of row I'm on matches either the second or second to last entry. So I want to expand this polynomial using my binomial theorem. I like to start by writing it out in general. So this is my way of kind of giving myself some direction. So from 3, choose r. Remember, r we're just going to use as a counter just to keep track of things. Times our first term, which is going to count down from 3, and our second term, which is going to count up from whatever r is going to be at any given time. So let's do that out. I have from 3, choose 0, 1 to the 3, 2x to the 0. I'm going to do that for my second term. First term counts down, second term counts up. And then my third term, First term counts down, second term counts up, and then my last term, first term counts down, second term counts up. So you notice I know when to stop, not just when I get to x cubed, but because my n and my r match. So simplifying this, I'm going to get 1 plus, using Pascal's triangle, it's a third degree polynomial, so I'm going to pull my coefficients right off of the third row. So I have 3 times 1 is just 1, or it's just 3, times 2x. And then my coefficient is 3 times 4x squared, and then 1 times 8x cubed. So simplifying one last time, get 12x squared plus 8x cubed. And that's all it is. It's just following this algorithm, plugging in, changing the exponents as we go. Well, we can actually expand this a little bit farther and talk about the binomial theorem for negative exponents and rational exponents. We have to be careful. This is no longer a finite series. This is an infinite series, so I have to give you a stopping point in a problem. The other thing that we have in these problems is this designation for the absolute value of x. For now, at this point in the class, we don't have to worry about these. For now, we're just being formal. If you were to pursue calculus further, or pursue calculus, further in college, get to talking about sequences and series in more depth, you would talk about something called Taylor and Maclaurin series, and that's effectively what you're looking at right here. So that restriction that I just highlighted in green is talking about those Taylor and Maclaurin series restrictions, which you'll study later on, but we're not going to worry about them here. This formula looks gross. It's not as bad as it looks. The first thing you might notice is that these two formulas are very, very similar. For my negative exponents, I'm adding every time. You see my pluses in here. Whereas with the rational exponent formula, I'm subtracting. You might also notice that, maybe if I look at this term, for example, I have a second degree term, so the degree of this term is 2. I've got 2 factorial, and I have the product of 2 consecutive integers. 2 consecutive integers. And that's true for my third degree term as well, right here. I have degree 3, I have 3 factorial, and I also have 3 consecutive integers multiplied together. Likewise with the rational exponents, except they're no longer integers because I'm dealing with rational numbers. But you still see I've got degree 2, 2 factorial, and the product of 2 numbers. Degree 3, 3 factorial, product of 3 numbers. So my example is to expand 1 over 1 minus 2x squared all the way up to x cubed. This doesn't look like a negative exponent yet, but we can write it that way, right? We can write this as 1 minus 2x to the negative 2, which means we can use our formula. First term is always 1, it's always equal to that first term in the binomial, plus 2x, so that n is always going to match the exponent, just the number, not the sign, right? We don't care about the negative here right now. Plus, so here we go, right? My x squared term is going to be 2 factorial, and it's the product of 2 consecutive integers starting with whatever exponent I was given. So I'm looking at x to the negative 2, my term to the negative 2. So I'm starting counting at 2 times 3. I do that again for x cubed, right? So for x cubed, I have 3 factorial, 2 times 3 times 4, the product of 3 consecutive integers, starting at whatever that power was that I was given. So simplifying this, 2 times 3 is 6, 2 factorial is 2, 6 divided by 2 is 3. 2 times 3 is 6 times 4 is 24. 3 factorial is 6, so I have 4 x cubed, and so on. Actually, not and so on, because I told you to stop at x cubed. So there is my expansion. This could be an infinite series if we want it to be. I could tell you to go up to whatever point you wanted. But I have to give you a stopping point here because my degree of my polynomial, my -2 here, doesn't actually give me an accurate stopping point. And it has to do with the way that we've defined our formula to tell from the ellipsis here that this is an infinite series.